Good evening, everybody. How's everyone doing this evening? Bad? Well, you're going to be doing great after this talk. Let me put it to you that way. Well, welcome, everybody. I'm Dr. Billy Tietz. I'm the director here at the Vanderbilt Dyer Observatory. And it's a pleasure to welcome all of you all up here. How many first-timers do we have here this evening? Big welcome to everybody. Okay. But thank you all for returning. Thank you for the newbies coming in. It's always a pleasure to have every one of you here. So before we get started, I just want to do a couple of announcements. So over the past year, Dyer has increased its educational outreach to the community. We've done field trips for nearly 1,000 MNPS students, and we're hoping that we're going to be able to continue to increase that number every year. We just completed a teacher workshop where we worked with K through 12 teachers in workforce development for microelectronics, and we're hoping that we're going to have many more of those types of workshops coming up in the future as well. So if any of you all are teachers or know teachers or have ideas, come talk to me. We'd love to hear those ideas. And we want to do even more with our students in our community, and we're going to be doing fundraising pretty soon. And one of the items that we would love to eventually get is a brand new digital inflatable planetarium. I know Dr. Erika has done the planetarium. Oh shoot, how many years has it been now? It's a lot. Yeah. If you had a nickel for every student that went in your planetarium, oh my goodness. So yeah, we want to follow in her footsteps and continue doing a lot of outreach into the community. So keep your eyes and ears peeled for that. And also keep an eye on our website and our social media, because we've got more events coming up in the year, whether educational like this, whether our signature events like our telescope nights, or we even have cultural events coming up. We have Bluebird on the Mountain concerts, we have the Nashville Opera coming up in September, and we've got a few other things planned that we haven't done before. So again, if you haven't followed us on Eventbrite or any of our social media, I'd highly recommend that you do so, because we got a lot we're going to try to pack in these next few months. So for the program for this evening, we're going to have a wonderful talk for about 45 to 60 minutes, and then we're going to open up the floor for a little bit of Q&A. We are also live streaming to YouTube this evening so that folks from afar are able to enjoy the fabulous Dr. Erika Grundstrom. And if you're watching us from YouTube, go ahead and post questions into the chat when you get them. And at the end, we'll read those aloud so that everyone here can hear it, and then we can get an answer to those questions by Dr. Erika. And then after the program, it looks like the skies are going to be clear. I'm keeping my fingers crossed. We're going to try to do a little bit of telescope viewing, but we'll give you an update at the end of the program. And you know, even if it does cloud up and it's your first time here, you got to go up and see that telescope. It's really fascinating. It's been here going on 73 years now. It's never disappointed. So, so with that, let me introduce our speaker for this evening. Dr. Erika Grundstrom is Vanderbilt University's Director of Astronomy Labs and an experienced educator whose kids may have had as who kids may have had as a teacher at Vanderbilt's program for talented youth. Do you still hold the record for the longest serving teacher there?
White.
Okay.
Not quite.
Okay, close
But
enough though.
close.
Yeah.
15 years.
Wow.
So
That's impressive. Or the kids may have seen her with the inflatable planetarium around the Nashville area. But as a kid, she lived on a farm close to the Canadian border where she thought the Northern Lights, something we hardly get to see down here, and that was just kind of a normal thing for her. But obviously, totally awesome. But it was learning about the constellations and the mythology with them that sparked a love of the stars, and then Star Trek: The Next Generation. Anybody else here a Trekkie? All right, cool. That set her apart. That set her on a path to being an astrophysicist. So when not astronomying, she loves to partner dance with her hubby and then hang with her 2 kids. So let's give it up for Dr. Erika Grundstrom.
all right, thank you, everyone. So I am really excited to talk to you today about extrasolar planets, because this is one of the things that is so exciting about astronomy today. So we are finding planets going around other stars. And of course, me being a Star Trek, especially the Next Generation fan, I'm always thinking about aliens. And it is one of the big things that astronomers do kind of think about, is thinking about life elsewhere. And we have a lot of data so far, but there's still so much more to learn. We will be looking at the kind of whole collection of data that is available freely for everyone to see through, and it's funded through NASA. So it's funded through your tax dollars to help support this. It's run through NASA and the Jet Propulsion Laboratory. So I have several friends who've worked on especially our Exoplanet Archive, which we'll be talking about pretty thoroughly here. And I love to teach about it. So there's a few things that astronomers think are just really amazing right now. One of them is extrasolar planets. The other one is gravitational waves. And that is something that other people can talk about. I want to talk about the planets. Let's talk about things that could possibly be visited by us sometime. Maybe not you yourself, but humanity going to go visit. So a couple of things just to look at. Looking at terminology, just really quick. So you could call it a planet going around another star, or maybe it is a planet-like thing that is just floating out there in space. It doesn't have a star that it's going around, whatever, free floating. So, but it has characteristics of a planet. So that's a mouthful, right? So then we go to extrasolar planet. Well, that's still a mouthful. So then we go to exoplanet. So you can use any of those kind of things to talk about planet-like things that are not going around our own sun. And that's why they're extrasolar. So, because, well, astronomers don't, sometimes we have really interesting and cool names, and sometimes they are a little bit boring. So we just shorten things. We keep shortening it. It's another thing with like a supernova, which is big, and then nova, which is new. And it's Nova Stellarum, which was that's new star. So we've got these different words. Or we have, telescopes like the Very Large Array of telescopes. And that is its name, the VLA. So I don't know. It's sometimes kind of, our naming is a little bit odd sometimes, and sometimes a little fanciful. So anyways, we're going to be thinking about planets going around other stars, or maybe free floating out there. We want to be thinking about what sort of data do we want to know? So I want us to be thinking about this, and I'm going to ask you to do participation. So you're going to be taught in this talk today, you're going to be talking to other people, and you're also going to be hopefully using a device. But I also have some paper for some people. So if you want to participate in doing some things, and maybe you're on the Wi-Fi here or something like that, we're going to do we're going to first start, and those of you online who are live streaming this can do this totally. We are going to be doing a word cloud to start with. So if you want to get your phone out, ready to go, to take a picture of a QR code, or to get or to type into your browser, whatever you want to do. Hopefully, I've made the QR code big enough for you all. Okay. We are going to be so I want everybody to go to this QR code, or you go to, it's Poll Everywhere. So it's POLLEV.com/Erika Grundstrom 608 is one of the things there. You can join by text. We're there. This is just the stem to our questions. It does ask you a lot of times if you want to put in a name. You totally don't have to, okay? Or you could, or you could be like, do something funny that I can know about. So our first one, we, as curious people, what are some things that first, so we're going to be looking at we're going to do 3 different word clouds. One, we're going to be thinking about what do you want to know about the physical characteristics of a planet? And then we'll think about orbits, and then we'll think about the host star. So our first one is this, and I think I can get this to show here. So it should be, let's see, oh, activate. Here we go, present. Okay. So what kind of things would you want to know about a planet itself? If you want to have multiple things in your answer, you should put a comma in between, but don't put any spaces. Like maybe you want to have like 3 words or something like that. You like concatenate, you put them all together. Okay. So this is our first thing. So what would you want to know as a curious person? What would you want to know about the planet? Talk to each other. Like maybe see like what do you think you might be able to do? Or what you might be interested in. So I might go back to I might want to make it so you can see the other thing. All right. Got them on there. Let's try that out. If you were like successful, you can like maybe give me a little thumbs up or something like that. Cool. Yeah. Talk to somebody else. Talk to if you're done, talk to the person around you. Make a friend. Oh yeah, physical characteristics. Ooh, look at you guys. Here's our word cloud so far. Cool. So our biggest one, it looks like definitely atmosphere. People are really curious about atmospheres. Of them, temperature also looks really big, right? Water. You can also see where some people maybe have maybe put in some spaces in their answers. Or something like what color is the dirt? Like geology. Like, does it have moons? I see moon and moons there. So mass, some gravity, oceans, liquid. So yeah, like, and also other differently, like does and ever are maybe parts of, sentences. Remember, you can't put any spaces in there and have it be a word on there. So cool. All right. So that will be, you know what I'm going to do? I'm going to 4 and take a little screenshot of that. I'm sure there's another way I can do this, but anyways, so we got that. Okay, so we've got that one to think about. Now, let's think about the orbit. I think, did it go to the next one? Okay, it did. Good. Just want to make sure. All right, so what would you want to know about a planet's orbit? Like if we're talking about planets going around other stars, what sort of things would you want to know? And so go ahead and put stuff in. If you're not going to answer for part of this, talk to somebody else, right? Think about what sort of thing, discuss with somebody. What kind of things would you want to put in there? Remember, the orbit is like how it goes around its star, or even is it free floating or not, right? That could even be a thing. Try and talk to at least one other person about what you've written down, besides the people that you're already here with. across the aisle, behind you, in front of you. Let's see. All right, I think we might be ready enough to try. Woohoo! Awesome. So people are very interested in how long the orbit is. Now, length, is that length of time or is that length of distance, right? So that, one of the things about science is you're always trying to make sure that you're incredibly precise with your wording. So we've got different things like, we've got rotation, we've got ellipse. So is it an ellipse, which means like, is it a circular orbit or is it not a circular orbit? And that's what eccentricity also kind of means. Distance from star, I like people like putting that all in one thing, right? Nice. How consistent is it? That's kind of awesome too. And like, are there moons involved again? And is it stable? So what's it around? Awesome. So these are all really interesting, useful things to think about. And we're going to be talking about what actually is out there as well. So, okay, I'm going to take this one too. And now I see there's wobble in there. Nice. Light side, dark side. Dark is probably up there somewhere. Cool. Okay. So then our last one that we want to think about is, what do you want to know about the planet's host star? Like the thing it is going around. So try talking to other people too if you want, like before you put in an answer, or you'd be like, how do I put this in here? Like, this is a lot of words. So try that. Oh, sorry, I went to the wrong page. Sorry. All right. Response. Yes, look at this. Awesome. People have got things that would be great to look at. So temperature, of course, of what kind of temperature is the star that this planet is going around, because that totally affects everything about the way that an atmosphere or anything would kind of generate, or even like what kinds of planets might form. So that's really important, like size, the age, or what stage is it in? Is it a red giant already or not? Do we even care about extrasolar planets going around red giants, which are dying stars? So yeah, like temp, how hot, like a lot of that. I don't know if greatest of all time is like one of those things, but size also, that's an interesting thing. Like there's a lot of, or size is a really big one right there. And are we talking about size width, like or radius, or are we talking about size mass? Because those are both incredibly important things, but they're also very different. So it's one of the things that we're trying to make sure that we're really precise and careful with our terminology. Also, I like the composition kind of thing in there, and like distance from Earth, those kinds of things are really great. So let's see. I'm going to take another screenshot of this. It's the quickest way to get, screenshots are the quickest way to get things in. So, to something. Okay. So, we're going to exit that. Great. Okay. So, as our curious people, we are looking at these different things. I can't get that up quite yet. We also are going to want to compare to our own solar system, right? So when we talk about extrasolar planets, we need to be able to have a way to, we're going to talk about all those things that you kind of put up there, but we want to be able to compare it to something that we know about, or at least kind of know about. Yeah, right, like our solar system. So one of the things I like our sun. So one of the things I like about this particular diagram is this is actually from a user on Wikipedia who made this. I love them because they're Creative Commons licensed. But anyways, these are accurate colors and accurate sizes. They're definitely not accurate distances from each other. Right? They're so close. So one of the things that you should notice is up there on the upper left where there's kind of like that white splotch there. What's that? The sun, right? That is how big the sun is compared to these other worlds. And then one of the other things you might notice is that what are the two, first of all, I suppose I should kind of be looking at this here. First of all, what is this one up here in the upper right? Jupiter. How do you know? Yeah, right. Largest. It's got the red spot. Very colorful. That one? Saturn, right? I love Saturn. It's an awesome world. Exactly. We know it because it has a ring.
On Saturn because then don't never ever go inside Saturn or Uranus because then there would be diamond rings.
Oh yeah, never. So we've got our friend up here who's talking about how we should not go in Saturn or Uranus because they have diamond rain, right? And that is, as far as we know, very true. That's what our models show us can happen because there's got to be condensation of something, right? Because things get really, they're hot in the middle, and then they get, then it gets cool when the atmosphere touches space, right? And so it gets cool, and so then things got to rain down. And so on Saturn and Uranus, that rain isn't necessarily water. It is carbon, and really squished carbon. And so that's diamond. So that's why we say it has diamond rain. Also, what are some of these, what are these like little things here? Moons, yeah, exactly. And these moons are the right size compared to these planets. This is awesome, right? And then let's look at the ones over here on the right, the kind of lightest colored ones there. Which ones are those?
Uranus and Neptune.
What? Yeah, Uranus and Neptune, right? we got our expert here. Now, look, I have an 8-year-old and a 5-year-old, okay? So like we're cool here. So anyways, notice, are those the colors you're used to seeing with those? No, especially which one? Yeah, and then we usually think of Neptune, right, as being really blue colored, right? The thing is, that's actually artificially colored. And so, yeah, and these are all the real colors. Yes, so these are all the real colors. And yeah, they're colored bluish, greenish because of methane absorbing all the red light and reflecting bluish and greenish light. But Neptune really should not be that blue color that we think of. But it's so cool to think of as Neptune as a blue color thing because what's Neptune the god of? Yeah, the ocean, right? And the sea. So then that's what we think of as blue, and so that makes like lots of good sense. However, when you actually like look at it with like the right filters and natural eye color, this is what they look like. So maybe not quite as cool, but still amazing worlds, right? So one of the reasons I bring this up is you should be able to think of at least a few categories, 2 to 5 categories, that things in this image could fit into. So I want you to discuss with at least one other person, what categories do you think those should be? Like which ones seem like they might be twinsies or should be grouped together? Okay, go. Talk to each other. Go. So I'll say I got a little, like, I love how much talking there is. I want to point out, like, somebody was asking me here, like, where's Pluto? It's actually right there in the lower right.
Wow.
Right there. That is the size of Pluto in comparison to all these other worlds, right? So, somebody that I haven't, well, okay, somebody give me one of the categories you think, like, or like a couple of, like, groupings or twinsies or something like that. Yes. Gas giants? Okay, cool. Which ones go there? Which ones would go there? The big four? Cool. Yeah?
Dwarf planets like Pluto and other ones.
Yeah, so dwarf planets, and that's actually all these things that are right here, down in the lower right. Those are the dwarf planets compared to that. So we've got gas giants, we've got dwarf planets. Yes?
Jupiter, Saturn, Uranus, and Neptune. I'm gonna put them in groups.
Okay.
Jupiter and Saturn, Uranus and Neptune, Earth and Venus, Mars and Mercury, dwarf planets, and the moon.
Oh, yeah, and the moons, right?
Planets, moons, and the moon.
Right. Awesome. Okay. So what else can we find? What's another category that we've got here that we haven't put a name to yet? Rocky ones, right? So rocky worlds, those are our four, well, a lot of people like to put the moon in with it too, right? So Mercury, Venus, Earth, and Mars, and the moon. Those are all our rocky worlds. You don't have to call them planets. You could call them worlds, right? It's a lot more inclusive. Okay? So we've got our rocky worlds. We've got our dwarfs. We've got our giants. But we could subdivide the giants. And in fact, planetary scientists totally subdivide these giants. Yes. Right. Which one?
I'm gonna.
What's one of the groups?
Say if you divide the giants up, you'll make Uranus and Neptune, Jupiter and Saturn.
Yeah, Uranus and Neptune are one. Those we call ice giants.
I knew that.
Yeah, right? And then, yeah, awesome. And then we've got our gas giants because they have different compositions. Okay? So Jupiter and Saturn, they have a lot of hydrogen and helium in their atmospheres, along with a bunch, with some other stuff too. But like they have a lot of hydrogen and helium. They do also have what we call ices. So ices in space are water ice, ammonia ice, and methane ice. Because water ice, that's hydrogen and what? Hydrogen and oxygen, right? Methane, do you know what that is? Hydrogen and carbon, right? And what about ammonia? Hydrogen and nitrogen, right? So we got carbon, oxygen, nitrogen, three of the most abundant elements in the entire universe. And the way that we know that they're really abundant is we look at the light coming from things in space, like space clouds, everything in space, and we see those three are incredibly common. Because they have fingerprints. They have fingerprints in the light that they reflect to us or emit to us. So Jupiter and Saturn are the gas giants that have a lot of hydrogen and helium, and and they're big, right? Then we've got Uranus and Neptune, and those are the ice giants. And so they have some hydrogen and helium kind of around them, but not very much. They have a lot of those ices. So water ice, ammonia ice, methane ice. So then these make up what we call the different exoplanet types. So we have rocky worlds. So they have, they're made of rock, silicates especially, and, iron and nickel and things like that. That's what's in the upper right. Far left is gas giants like Jupiter and Saturn, a lot of hydrogen, helium. And then we have Neptune-like. So our kind of standards are Earth, they're Earth-like or Earth-similar, Jupiter-like, and then Neptune-like. because we don't want to say they're Uranuses or Uranus-like or like Uranus-like, right? So Neptune rolls off the tongue a little better. And so we've got those, and then there is another type of world that we do not have an example of here in our own solar system, and that's the super Earth. But we're going to be looking at some data to show that that's actually a very abundant type of planet that's out there in the universe, or in our galaxy especially. So this is a graphic from NASA and JPL, or Jet Propulsion Laboratory / Caltech. So I wanted to make sure that you saw that kind of thing. So we've got that. We've got our planets and our groupings. So gas giants, ice giants or Neptunes, and Rockies, and then we got the super Earths. And so there's kind of like it's the difference between, like, you go up Rocky, but you have the ice giant, and like where's that boundary right there? So yeah. Then when we compare to our solar system, I also wanted to kind of show this one. And actually, Natalie, we can go ahead and start handing out that handout. So we've got a handout that's coming around to folks that's going to have, because you're going to probably want them, have the data for all of the planets and also have this picture. And one of the reasons why I like this one is, or there's two reasons I like this one. One, that it has the correct sizes for all of the different worlds, and also has like things like the asteroid belt and the Kuiper belt where a lot of the dwarf planets are. But it does have on the bottom, I kind of zoomed in a little bit on it, it has the distances, like how far apart they are from each other. So our rocky worlds in our own solar system are pretty close. Right? They're all within what we call, or within 1.5 astronomical units, right? Yeah. So an astronomical unit is the distance between the sun and Earth, right? So whenever I say, like, if I said 1.5 astronomical units, you would think, okay, that's 1.5 times farther away from the sun than Earth is. Right, and that's Mars, exactly, right? And so, oh, by the way, the handouts, there are 2 pages to the handout, okay? The double-sided didn't work quite the way we hoped. But anyways, so there's two pages to that. One is this image, and then one is a data table. Okay, so the other thing that I want you to think about is, like, okay, Jupiter. It is 5.2 astronomical units away from the sun. So what do we think? Like, or what, like, when I say 5.2 astronomical units, what should you be thinking? Yeah, 5.2 times farther away, right? So then the big thing to notice with this is our rocky worlds are all pretty close, and then our giant worlds, we've got Jupiter and Saturn. Remember, those two are twinsies. Those are our gas giants, and then our ice giants are a lot farther out. There's all sorts of things to do with formation scenarios and stuff like that that are interesting there too. But, you know, I don't really need to talk about that super a lot. But one of the other things I wanted to point out is that Pluto is on this line. I love Pluto. It is actually one of my favorite worlds in the entire solar system. Notice I said world, right? It is currently classified as dwarf planet, and there's lots of things to be said about that. But one of the things that I like about it is that it's really about having it as its own category, is that it helps describe what's going on in that category. That is why we have categories. That's why we name them. And so a lot of people in, planetary sciences like to talk about things, like to talk about planets with an adjective in front of them. They are a gas giant planet. They are an ice giant planet. They are a dwarf planet, or world. So, or, they're a moon or something like that. So anyways, the thing with Pluto, though, the thing that I don't like about this one is that if you look at your data table that I have just handed out to folks. And actually, I will say that folks at home, I actually have the handouts for you in a Google Drive folder that you can take a look at. And people manning the YouTube, let me know if there are issues with people saying they can't get into that folder. Okay, Tommy, can you just take a quick look at the YouTube, the comments, and see if people can get in that? So I want you to look at that data table, and I want you to look at Pluto. So it's included because it has some interesting things. But what do you notice about the distance from the sun on that one? Yeah, it varies, right? Like, it's a pretty big difference. There's a big difference between 30 times farther away from the sun than we are and 50 times farther away from the sun than we are. So folks at home, by the way, this should be the solar system data table in that Google Drive folder that you can take a look at. So that is a thing that I always kind of get a little irritated about when I see these things that have Pluto on them, because they don't show the range. What they're showing is they're showing the average distance from the sun, and that's 40-ish, right? 30 to 50, average is 40. So it is a thing to think about with an orbit of a world, a planet. Is the orbit circular or not? Right? So this is something that if we are looking at planets going around other stars, we have to kind of consider what's going on with that. And that does play a pretty big role in when we look at our data sources. So all that kind of leads us up to looking at data sources. So folks at home might have a little bit easier time of this than folks here, but I am first going to show one graph, and then I will show you where you can find the data, and then people will be able to mess around with your own device and find the data if you want to. Okay, so let's say as people were thinking about, they were thinking about temperature. You know, when we're thinking about planets, people really liked thinking about temperature, really liked thinking about the size of the world and distances and stuff. So there are these data sources and these big giant data tables. And so I am going to actually show you real quick one of my favorite ones on here. This is the NASA Exoplanet Archive. And so this is a table that has 5,972 rows. So that's 5,972 planets. And it has it has a lot of columns, right? So it has a lot of data. You see some of the columns are blank, right? Or, you know, some of the things just don't have any information, like especially right over here. But a lot of them do have information in there. And we're going to look at some of that in a little bit. But this is from the NASA Exoplanet Archive, and it tells us how many confirmed planets that they are keeping track of. One of the reasons why NASA and the Jet Propulsion Laboratory and Caltech decided to go ahead and do this kind of thing is because there is a lot of people discovering extrasolar planets, and it's really nice to have the data all in the same format. If you're trying to make graphs and stuff, you want it all in the same format, like, you know, with what's going on, and like everybody has the same column is distance from its parent star or host star. So like that, we need that kind of information. So we are going to mess around with that. It has, you may notice that it is maybe not the most updated style of website, but it works. And that is sometimes more important than it looking pretty. So, I mean, it looks pretty good, but it still is maybe a little bit, it's not the like what current user experience looks for. So it's got a whole bunch of, data things. There's a lot of numbers on here, how many there are by certain radii of different worlds and stuff. So we've got, there's a lot of information, and then you can get to this data table. So I'll show you how to get to that in a little bit. But we're going to be working with some things with the data tables. But let's say that we want to just go ahead and we're going to make the most simple graph, or I'm going to first show the simplest style of graph that we have, which is a histogram. So that means that the horizontal axis is some variable that is of interest, and then the vertical axis is how many things there are in that, of that variable of interest. So our first one that we're going to look at is planet mass. So there's been a lot of data, a lot of stuff done. Let's look at what kind of masses there are of the different worlds. So you're going to want to make sure that you have your data table accessible, because you want to be able to look at that. One of the things I have done with this data table is I have put the mass of them in both Earth masses and in Jupiter masses, because we like to think of things as either Earths or Neptunes or Jupiters, but especially with extrasolar planets, there was, especially at the beginning of finding extrasolar planets, things were more Jupiter-y mass, and so it was a lot easier to deal with Jupiter masses. And so that's one of the things that extrasolar planet scientists do, is look at Jupiter masses. So we're going to look at the distribution. What is the for extrasolar planets found so far? What is the distribution of extrasolar planet masses? So the horizontal axis is planet mass in Earth masses. And I know that that's a little bit small for folks. And then the vertical axis is how many there are of those masses. Now, you may notice that there is one thing here that is gigantic. It has 4,200 planets in this one little bin. But notice that it is really pretty, it's pretty low mass. What is the mass of Jupiter in Earth masses? Yeah, 318. Right. And so 1,000 is right here. So we are all 1,000 Earth masses is already way more massive than Jupiter is. There is no world in our own solar system that is like any of the things that are on the right. These are things that are 2 to 30 times the mass of Jupiter. So this kind of graph is not that useful because everything is in one place, right? So it's not that interesting to look at. So then, whenever we're doing things, especially in astronomy, a lot of times we have to look at big numbers and small numbers together. So we're going to have to look at a logarithmic axis. Okay, so we also call this the powers of 10 scale. So instead of having the top row, that is a linear axis. And so every this little bit is another 100, right? But if you look at the bottom axis, it is not the same. It still ends at 1,000, but it's done in a very different way. So the first one here, this is 0.1, then this is 0.2, 0.3, 0.4, and then it kind of scooches in there, 0.5, 0.6, 0.7, 0.8, 0.9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20, 30, 40, 50, 60. So you're doing things in powers of 10 because then you can show small numbers and big numbers at the same time. The thing is, it is sometimes hard to interpret those kinds of graphs because we are used to linear stuff. That's what we use, right? You know, if you're going in a car, you're driving along, you're not doing logarithmic distances, you're doing linear distances. So that's not what we're doing. So Natalie, next one, coming out, the histogram one. We are going to logarithmic this graph. Exact same graph. See how like all the numbers like are the same font and everything like that? Exact same graph. But now it's the powers of 10 graph. Now you see that, oh, you're like, oh yeah, maybe all these planet masses are totally spread apart. Like there's a big range of masses. No, there is not. Remember, there were 4,000 planets that were within this one box of like 0 to 100 Earth masses. So that's why I also have on this, and so I've got we've got another set of handouts coming, and so you can look at it your own self. Again, people on the live stream, go to that. If you go to that Google Drive folder, you should get the histogram one. So what I've put on this one is I have put little lines where Earth is, where Neptune is in masses, and where Jupiter is. The thing is, all three of those were in that one big tall block on the first graph we did. Now we get to see a little bit of spread outness, but you might think that there's more of a range of data than there actually is. You got to be really careful about the logarithmic graph. This is not only a thing for extrasolar planet information or astronomy information. Logarithmic graphs are shown in the general public all the time. When you're looking at the New York Times or Wall Street Journal, if they're showing you or any of these different kinds of things, and they're showing you a graph, you got to be careful of what the axes are. And you will know by looking at, so by the way, the vertical axis is linear, but the horizontal axis is what we call logarithmic. And I've put a key over on the left with what each of those things mean. So log 10, this is the logarithm base 10, because there's also the log base e, log base 2. You could do all sorts of different things. We're doing log base 10 because we're thinking powers of 10, right? 10, 1, 10, 100, 1,000, 10,000. So each of these things, then we see, what would you guys say is the most dominant kind of planet? Look at where Earth is, look where Neptune is, look where Jupiter is. Probably super Earths, maybe. Like maybe Neptune-ish, but probably more like super Earths. Given the data that we have so far, there are more super Earths out there than there are Jupiters. Jupiter-like worlds, right? We don't have any information yet about distance on this graph. Like that is not part of our thing here. This is only looking at mass. But you also see that there's a hump there at Jupiter-like worlds, right? So there's also a lot of those. What do we not see a lot of yet of our different kinds? No, gas giants are Jupiters, right? Well, definitely not dwarf planets, for sure. Like, I don't know if we've even seen anything like that. But what else? Terrestrials. Yeah, I heard that back there. We do not see many rocky worlds, right? Because Earth is our representative rocky world, and we don't have a lot of things here. But in our own solar system, half of our planets are rocky worlds. Right? Let's say we have 8 planets, right? And so we have 4 giant ones, gas and ice, and we have 4 rocky ones. But we don't see them yet. Yet. It all has to do with how we find things. So when you look at data, you got to be kind of thinking about like, oh, how, like, it may be that I see that the like super Earths are totally the most dominant kind of planet. But so far, like that's why whenever I say something, it's like for extrasolar planets found so far. Because we can only say something about what we actually know about, what we actually have data for. So we look at another histogram. That should be on the back side, or the second page. Orbital period. We did it again, right? We have got a lot of stuff down in that one corner over there. And this time we've got, it's about 5,200 in this one thing. But look at orbital period in days. Is there a world that has an orbital period of about 10,000 days? Yeah, Saturn-ish, right? So we're already, like if we get to 10,000, that's already Saturn, right? To say nothing, like, so again, we're going to need some logarithmic data, right? And that's why we have this one. That should be the second one that you guys see on there. And I have put these lines, okay, so that's like when you do your stuff, you can do that when you actually start working with, you know, some data, but like I have put those on there. They don't automatically come on there. I physically had to put them on there. But we look at Neptune, we look at Earth, and so I decided to do Neptune just because I thought that was like probably one of the farthest ones that would be interesting. But then look at Mercury. Mercury has an 88-day orbit. What do we see about extrasolar planets known so far? They have really short orbits.
Yeah.
Really short. Yeah.
I learned there was a planet called 55 Campri, and its orbit is only 18 hours.
Yeah, so like, yeah, exactly. 55 Cancri E, 55, or what, 18 hours, 55 Cancri B, or E, 18-hour orbit, right? So our data are showing us that we are seeing things that are close to their star, right? Like really, like we have got an observational bias here, right? Like we are seeing things that are close. And so then, like, what does that mean about the kinds of worlds that we might see there? Well, we're seeing a bunch of super Earths. We're also seeing some Jupiters. We're seeing various other things. But, you know, right now we have histograms. That means that we're only looking at one thing. We're not looking at it related to anything else. But a histogram is a pretty awesome thing. Love the histograms. So let's think about a conclusion that somebody could make. Most extrasolar planets discovered so far take about the same length of time to orbit their star as Earth takes to orbit our sun, and they're mostly Jupiter mass. Would you guys agree with that statement? All of it? A part of it? Talk to each other around you. And then what is your evidence? Okay, talk to each other. Go. All right. So let's do a little show of hands here. Okay. Totally agree. This statement's totally correct. I'm so happy to see that nobody has raised their hand. Great. So obviously we're going to disagree with part of it. What is one piece of evidence? Somebody from the back there, tell me about a piece of it that they disagree with and why. Yes.
The orbit time is not similar to Earth. Earth's is 365 days, and the average orbit time is about 10 days.
All right, or the biggest peak, right? Yeah, is around 10 days. And so we look at our graph in order to do that. And so, orbital period there, right? I mean, oh my gosh, right? 10-day orbits? There is nothing in our solar system that is like that, except for maybe the Parker Solar Probe. That is the closest thing that's ever been to the sun. So that humans have made. So, and survived. What about the other part? Mostly Jupiter mass. No? Why not?
Hot Jupiters are gas giants that are really close to their stars.
Yeah, and there is this thing called hot Jupiters, which are gas giants, which are really close to their star, because we obviously have to have some if we have a whole lot of things that are close and a whole lot of things that are heavy, right? Like Jupiter-like things, right? So do we agree with mostly Jupiter mass? What did we say was the biggest, was most of them? Super Earths, right? So, right? So, yeah. We could also do some data combinations and stuff like that. So, yeah. So we've got to just be thinking about some of these things. And I will say that I had, especially back a few years ago, people were saying, oh, our solar system is totally unique. There's nothing like it in the universe. But we haven't discovered, we can't discover that kind of thing yet. It is totally an observational bias. So, yeah. So anyway, it was so frustrating when I would see that. It was you do not have, everybody should put in front of their thing for extrasolar planets found so far, our solar system is unique. Maybe, but so frustrating. So anyways, there's one thing I wanted to kind of point out here, for extrasolar planets found so far, how are orbital period and orbital semi-major axis related? The thing is I can usually say, well, I keep saying, I've said things things that are, have short orbital periods, I might say that they're close. Well, there is a relationship. It's totally a relationship. So on the horizontal axis is orbital semi-major axis, so how far away this planet is on average from the star. And then if you go on the vertical axis, that's how long it takes to go around the star. And you see all the data there. It all just kind of follows a line. It follows a thing. And you know what that is? Physics. It's gravity. This is my favorite equation in all of astronomy. Okay, this is Newton's version of Kepler's third law. If you saw my moons talk that I did last year, I brought this one out too. It's totally the best one. And so most awesome equation in the universe. And so you've got orbital period on the left, and then on the right, your distance from the gravity source, and then also that's divided by the mass of the system. This works everywhere in the universe. This works with stars and planets and their planets. It works with planets and their moons. It works with planets and our satellites. This works with galaxies and other galaxies. This works for black holes orbiting each other. This works for anything that is doing orbiting. This works. It is amazing. And this is how we figure out mass in the universe. Because if we know how long it takes something to go around something else, and we know about how far away it is from the thing that is orbiting, we can figure out the mass of that object. And so, in fact, we have 2 planets in our solar system that don't have moons. Mercury and Venus. And so we didn't know what their masses were until we actually sent, like really well, until we actually sent spacecraft to them. Because we couldn't do this with every planet, every other planet and dwarf planet, because almost every dwarf planet has a moon, which is very interesting. We can figure out its mass. So we can do that kind of stuff. It's amazing. And with this really, really important, amazing equation, and for the most part, we don't need general relativity would make this worse. Okay, but we don't need that most of the time because we are usually not dealing with things that are going near the speed of light. General relativity is gravity. Okay, so, but all we usually need is this. So if we think about this thing, the period, orbital period, so how long it takes to go around, is definitely related to the distance from the gravitational source, so semi-major axis. That's what A stands for, is axis. And then, but mass is involved as well. So one of the things that we can do with the data, our data sources, is we can figure out also, let's add in a color with host star. So it's going to be the exact same graph. Remember that that one looked like that, right? Now we're going to add a color gradient. Okay? It's a little hard to see, I think, but you see that the darker stuff is above the line, kind of the dark blue, and then the reddish stuff is below the line. So the reddish stuff is the heavier things, the heavier stars, heavier parent stars, and then the bluer stuff is the lighter parent stars. And what that shows us is this shows us that extrasolar planets are also following Newton's version of Kepler's third law, which was devised here in our own solar system, and physics works out there in the rest of the Milky Way galaxy, which is amazing, right? Physics works. And so, like, we can add things when we have different visualization tools. And so here, I suppose I have a zoom in of that little piece there. So you can see some of those different, the color gradient, how it goes from one to the other. It's very beautiful. Yeah, so there are 3 data sources that I want you to kind of think about. There are 3 that are really great. So NASA Exoplanet Archive is one of them, and that was the one that I showed you with the big giant table. Then there is, so I'll go to the bottom one first. Exoplanet.eu is run by people over in Europe. And so it's essentially like the same thing as the NASA Exoplanet Archive, but it's run by the Europeans. And they do try and make sure that, both of them try and make sure that their data sets match with each other. Okay, so they try and make sure that things are cool there. So you can use either one of those. And then the middle one there is the NASA Exoplanet Archive grabbed in a data visualization tool called Filtergraph. All the graphs that we looked at so far are from Filtergraph. Filtergraph was developed by people at Vanderbilt University, people who, especially they're neurodivergent individuals who are part of the Frist Center for Autism and Innovation. And so they built it for astronomy, actually. So that was one of the things that was part of it. They built it for giant astronomical data sets. And you can put in your own data sets. Okay, you don't have to use just like this. This is an API grab for anybody who is familiar with that kind of things. It gets automatically downloaded every 24 hours, the data set does, from an API thing. But you could put in your own data set into Filtergraph. It is awesome. I highly recommend Filtergraph. But if you Google search Filtergraph extrasolar planets, you won't get the one that I made. I made one called Extrasolar Planets Astrolab, because I use this for my astronomy labs at Vanderbilt University, because that's what I teach or what I'm in charge of. So anyways, like, you can use that and you can figure out all sorts of awesome things doing that. So anyways, I wanted to show you a couple other things that I think would kind of help. And if you want to go to one of these things, you are welcome to do that on a device, especially those of you who are at home on the live stream that maybe might be interested in doing something while we're looking at stuff. So one of the other graphs I wanted to show that helps exemplify one of the things I think is really interesting in the database. So for extrasolar planets found so far, how are planet mass and planet radius related? So what's an equation we have that has both mass and radius in it? It's like that would maybe tell us something about the physical characteristics of a planet. Huh? I think I heard it. Well, it's not that gravity one. That's a different thing. Mass divided by volume. Density, right? So mass divided by 4/3 pi r cubed, right? So that's the volume of a sphere, because it's a sphere-ish. So with this, if you have a graph like this, you can get information about the density of your world, which would be really cool because with density, you can figure out kind of in general what it's made of, because rock is more dense than gas or ice. So there is a relationship with between what kind of planet you have, a gas giant, an ice giant, or a rocky world, and its density. So you should be able to see something kind of going on. So here is the graph, also from the filter graph data visualizer. And each individual dot is a world. But you might also notice something else kind of going on there. You see that there's some lines going on? Right? I'll kind of point that out. Like there's this one here. Sorry. And then there's kind of this one in here. And then there's this one coming over here. Okay. That tells us something important about the data that we have. Because if you want, let's say that all you have as information about your planet is its radius. You could, and you don't have mass, then you can't figure out density. Well, if you guess at what density it is, so let's say that something that is 1 Earth radius wide is likely a rocky world. So it should have a density of, an average density of 5.5 grams per cubic centimeter, or kilograms per cubic meter. And so then I can infer what the mass is. So if a planet is lying along that line, those 3 different kinds of lines, and what kinds of worlds do we have? Rocky worlds is one. What's another? And super Earth is a rocky world. Yeah, what else? Ice giants and gas giants, right? So here we have the ice giants, and there we have our gas giants over there, right? So we infer what kind of world it probably is if we only have one piece of data. If we only have radius or we only have mass and not the other. But the ones that are dots that are not on those lines, those are ones where we have both the radius and the mass. So then we can get like what its real density actually is. So it shows like the scatter of like what kinds of worlds are out there. So the, I don't know if you can kind of also see it's something that's kind of interesting that I always love to point out way over here on the upper right, that even though the world is like 100 times, so Saturn is 95 times the mass of Earth. So Saturn and then something that would be like Jupiter, which would be kind of right here, are about the same radius. And even something that is 10,000 times Earth's mass, which is like a whole bunch of Jupiters, is still the same radius. And that is because it's a gas giant, and so that gas just keeps compressing and compressing and compressing. It doesn't puff up. Unless it's really close to a star, like a hot Jupiter, right? So a hot Jupiter gets puffy because it has all that solar influx to it, which is, and so then it makes the outer layers get really big and puffy. So yeah, that is like a kind of a cool thing, and that tells us like what sort of data do we have and what sort of data do we need, because we would love to have both the mass and the radius, but it depends on what kind of data mechanism, what way we actually find out things are happening. I cannot get to, sorry, I'm having a struggle here. And I know we're about almost out of time here. And so when we think about ways to find a planet, there are a couple of different ways. Or the 5 major ways. This is from the NASA Exoplanet website. Awesome resource. Okay, I'm going to have a page of resources here at the end. But this awesome resource. So radial velocity is watching for the wobble. Transit is looking for shadows. Direct imaging is we just take a picture. Gravitational microlensing, that has to do with some general relativity. I'm not going to talk about that at all, but you could always ask me about it. And then astronomy is looking at, or astrometry is looking at minuscule movements. So this shows, as of this morning, how many planets have been discovered from each of those different kinds of techniques. And this is because this is from the NASA website. They have all the data. This is a really, really cool thing. If we're looking for shadows, it's easiest to find things that are big and things that are close, because if they're close, they also go around really fast. They go around a lot of times. So you can see you get a lot of data pictures. Radial velocity, you're watching for wobbling. And if you have a heavier thing, it's easier to see a wobble. So that's something that we generally find things that are close, and as we've seen from our graph already, and we see things that are big, heavy things. And so that's why I like super Earths and Jupiters. So there is another graph, and that I wanted to, it's our last one. Natalie, if you'll hand out that last one, that's our last little thing here. This is from the NASA Exoplanet Archive data visualizer. One of the things I like about this is it also has error bars. We love an error bar. And it shows on the horizontal axis is semi-major axis, so how far away that planet is from its star. And then the vertical axis is the planet mass. And so we see some interesting things on this. And everybody will get these as well. One of the things that I like to kind of emphasize is that correlation is not the only thing that is interesting. Because in fact, I think that the blank areas and the places where there are clumps of data are more interesting than anything else here. So, we see there are 3 things I want to point out here. 1, I'm going to point out this clump right here. Upper left, stuff that is really heavy and it's very close. My man, what are those called? Things that are really heavy and really close? Hot Jupiters, yes. Awesome. These are some of the first discovered worlds because they are heavy and fat and they are close. But we have nothing like that in our own solar system. These are things that are, if the orbital semi-major axis is like 0.1, Mercury's distance is 0.4, okay, 0.38 astronomical units. So these are things that are far closer than Mercury, like 4 times closer than Mercury is to our own sun, and they are Jupiters. This totally changed how people thought about the way the planets formed. So these hot Jupiters were some of the first things found because it's easier to find things that are close and easier to find things that are heavy or fat. Wide, I should say. And then we have this clump here that is super Earths and Neptunes. And then we also have a bunch of stuff over here that's kind of interesting. But then look at this over here. All this whole area right over here. Planet mass in Jupiter masses, our Earth is 0.0, according to our data table, our Earth is 0.003 or 003. So it's right about here. Oh, actually right about here, sorry. So you go over. So we do not have anything here kind of like what you would see in our own solar system for rocky worlds. Does that mean there aren't any? No. Why not? That's a lot of universe, yeah, but also why not? They're hard to find, right? Because we find that what are the easiest things to find? Close and big and heavy, right? That is not the, so essentially what I like to, the analogy that I like here, and this is kind of what I'm going to leave you with today. The analogy that I like here is that if you're in a giant crowd of people, it is really hard to find the toddlers, right? But it's really easy to find the basketball players because those are the ones that are like above everybody else. Those are the hot Jupiters in this. And then the toddlers are like, you know, our own solar system. That's the stuff in the lower right. That does not, the fact that there is nothing here does not mean that there is actually nothing there. This is just for extrasolar planets found so far. And then, you know, kind of the other interesting thing I like to show about this is a different, you know, this is the exoplanets.org or the filtergraph version. This is showing the different types of, the different ways we find the different discovery methods. The colors are the different discovery methods. So you could, if you want to, go to one of these resources and figure out what kinds of, you know, like look at what are the best ways to maybe try and find Earth-like planets. Well, if we kind of zoom in, it's this technique called microlensing. So here, if we had, like this line here is Earth distance. And then there's Earth mass. So I did it a different way. So only like these purpley ones, those are microlensing. But transit isn't there yet, and other different kinds of things. So we just have to be aware of what there is out there, and we have to be aware of how we're finding it. So whenever you look at data, you should always be sure of where the data are coming from. Like, what's your source? What's the observational bias that there might be? Like, is it only that you're finding the biggest things or the brightest things or the heaviest things or something like that? Or, you know, are the ones that are the loudest, the people that are the loudest, perhaps? Those are the data points that you have. What about everybody else? What about everything else? So just like kind of keep in mind what's out there and how you're finding it. So I want to leave you with some other resources that you might find interesting. The NASA Exoplanets website is amazing. It has for every single planet, it has a graph of the habitable zone that it has, or it has a diagram of that, and it has everything that the NASA Exoplanet Archive does, except prettier. So like it's all there. It's just like, yeah, it's definitely prettier. So, and then if you are really interested in habitable zones, then there is an applet simulation that it used to be JavaScript and now it's in another thing. It works on Flash, or it works on HTML5 and stuff. It is part of the University of Nebraska Astronomy applets. I really love that one. If you're interested in actually being a citizen scientist for this kind of thing, the American Association of Variable Star Observers, it's like the whole world, but AAVSO has a whole exoplanet group, like people who are not professional astronomers, but are great enthusiasts, can do contributions to extrasolar planet research, which is awesome because we need that kind of stuff. And then there is another kind of just resource, which is the Habitable Zone Gallery. It has a list of all the different kinds of extrasolar planets which might be in the habitable zones of their particular stars. So those are also really incredibly interesting as well. So those are some cool resources. And I wanted to also bring you back. I'm pretty sure most people took pictures of the data sources, the archives that you can look at. I'm going to have that up as well for you. And I'm happy to take a few questions. Thank you very much.
All right, thank you so much, Erika. Another fantastic talk. I learn something every time that you give a talk out here.
Thank
Not
you.
kidding, not just saying
I know
that. I
it.
really do. So.
I know it.
But yeah, let's take a few questions.
I know I ran a little over time, but hopefully that'll
Don't be
make
shy.
it so that viewing is better through the telescope.
Yeah.
I'm so excited. I'll say that
Wow.
the last time, 2 times I was here, it was cloudy. So
Well, while they were formulating questions, we had one online. Let me pull it up here. How much of the data distribution is driven by limitations of technology? For example, can we only see the big exoplanets?
right, yeah, and so that we
Okay.
did kind of address some
Yeah.
of that, and so really it is, and that's one of the reasons why it's so important to have things like the Kepler spacecraft that was up in space and was looking at one particular piece of sky for, well, it was nominally 3 years, but it went longer than that. When at least 5, still doing things, not, it's just can't point very well. So anyways, but it's looking at one particular piece of sky to try and get a really accurate census for as many things as possible. And so now we have the TESS satellite, which is a terrestrial Earth, or terrestrials and Earth. Yeah, so it's some sort of I cannot remember what that acronym is, but the TESS satellite is also trying to find Earth-like worlds, and so just trying to be really, really, really accurate and complete is really important. But the thing is like trying to get masses of different worlds is also really hard because you have to use spectroscopy, which means that you need a whole lot of light for it, or like either a really big telescope or and really, really accurate data. So, and it just takes a lot of time. All that takes time. So the thing is in order to confirm that we actually have a planet, we have to have a lot of observations of almost a complete orbit. And if you look at your data table and look at the orbit, like how long it takes to get to look to see Jupiter go around one time, like how long is that? 12 years. 12 years, right? So it's if we were trying to confirm that it's there, we would need at least 2 observations of it, or be able to see at least a couple of orbits. I mean, we're talking 25 years, or more, or 50 years to try and find some of these things that are a little farther away. So we just need, it's just time. We need to have some time. So, but 1995 is when everything kind of started, when the floodgates opened, which is very exciting. I was around for that. It was so cool. But we've seen there's already almost 6,000 planets found in just, these 30 years. So, yeah.
These 6,000 or so planets that we're talking about, are they all within our own galaxy? Is that correct?
Oh, yeah. So like the 6,000 or so that we've found so far, yes, they are all within our own galaxy. And our galaxy is one of hundreds of billions of other galaxies. And so if we just think about that, I mean, oh my gosh, right? That there are likely billions upon billions of planets in the universe out there. Because physics works, right? Newton's version of Kepler's third law works with galaxies interacting with each other. Oh my gosh. And so then that, gravity works. And so it does probably the same thing. It's amazing. And then there's a particular type of study, like microlensing studies, have a really good completeness thing, and that makes it seem that most of the planets or most of the stars in our own galaxy likely have a planet or more. Several planets. And there are and then one of the things that the NASA Exoplanet Pretty site talks about is how many planetary systems there are. So there's 6,000 planets, and there's about 4,700 systems. So that means there are many multiple star systems, or multiple planet systems, I should say. And there are also planetary systems that have 2 suns, like Star Wars' Tatooine and stuff. They definitely circumbinary planets. So pretty awesome. What else?
As soon as the Vulcans get here and give us warp drive, we're all set.
I know, right? As soon as the Vulcans get here and give us warp drive, we're all set. Totally agree. I'm waiting for it. You know? Yeah. Well, yeah. So true. So.
What do you think about the Big Bang Theory?
Oh, what do I think about the Big Bang Theory? I think it's awesome. And there's a lot of interesting data that shows that our universe is not infinitely old. And that is kind of the most important thing, that we have the technology to see some really old things, but we don't see them. And that's one of the ways that we know that we had to start from something. And then there's a lot of evidence about expansion and stuff like that. So there's really, really cool things out there about that. So, but that doesn't necessarily mean that there's one piece of that maybe like gravity has changed, like the way that we, do the gravitational, like my favorite equation, right? That the G in there may have changed over time. That could have happened. We still don't know yet, right? But it's really, really, really hard to see a lot of that stuff, because it is the only stuff that we have is really, really far away. And then you need really, really powerful telescopes in order to see that, and a lot of time to look. And everybody wants to use those big, powerful telescopes to find things like planets and, and colliding black holes and things like that. So it's, always a trade-off. So, yeah. Eleanor?
If there is such a thing, okay.
It's for the people at home.
Okay, gotcha.
Yeah.
If there's such a thing as solid planets and gas planets, are there liquid planets too?
Ooh, that's a great question. So there are, now I will say that when we talk about gas planets, we have to always remember that they do have a solid core. Right, they do have a piece of their insides are so smushed together that it's so dense that you would be able to walk on it. But by the time you get down to that kind of density, you would totally be crushed, right? So you wouldn't want to do that. But there is a solid core. So there's always a seed that it kind of comes around. But there's likely things like water planets where essentially they had so much ice and it's in maybe a part of their planetary system that it can be warm enough that it turns liquid, and so then you have water worlds, and so they wouldn't be liquid throughout. There would be definitely some solid stuff in the middle, but yeah, you could have like a surface that has a lot of cool, that kind of thing. So yeah, awesome. Yeah.
On your Kepler's law plot. Your color plot, there are some planets that seem to break Kepler's law.
Oh,
like
yeah,
they're outside of their color,
the
where
gradient,
their color
right?
should be,
Yes, yes. And so the thing that I should have on there is I should have error bars, and so I've looked at so one of the things you can do with pretty much all these data visualizers is you can, if you see like an outlier like that, you can click on that dot and you can see information about it. And so especially the one in the lower left there, that kind of greener one, that one was discovered via microlensing, which doesn't always give very good periods or semi-major axes, because it's a single time snapshot, and so you don't know if it is at its farthest point or not. So there's some issues with some of those, and so they really should have a lot bigger error bar on that. So I kind of wish that I had put those on, but it makes the graph pretty messy sometimes. So yeah, but what you want to do is, like, for those outliers, those sometimes show you some of the most interesting physics and the most interesting investigations of your observational bias. So there's kind of very exciting. So it's like, what's wrong here? Or it could also be just a transposing of a couple of numbers when it was entered by the original. Because what they do is they grab from papers, and so maybe somebody put the wrong numbers together there. So that could also be a thing, which I have found that kind of stuff, like in there. Or they could be huge planets. True. And with a really, really low mass star also. And so, yeah, so that could be a thing too.
All right, well, let's thank Dr. Grundstrom for another fascinating talk. And if you have more questions, she's going to be sticking around for a little while, and I'm sure she'd love to take those. The telescope is open. The moon is up. It's near full moon, not the best time to observe it, but hey, it's still the moon. It never disappoints. So if you'd like to go up and check out the moon, please do so. Just go down the hallway there and hang a sharp left and go up the steps. But again, thank you again, Dr. Erika Grundstrom, for again, just another wonderful talk. So, and thanks to everybody at home that's watching us on YouTube. Hope everyone has a great evening.